Hello everyone, and welcome to the online lecture for college algebra. In this video, we're going to cover section P3 of your book on rational exponents. Now, before we get started, we should probably explain the title a little bit to make sure we're all on the same page and discuss what we mean when we say rational exponents. So the set of rational numbers in mathematics are numbers that are essentially one integer divided by another integer. So what we're really talking about in this section is fraction exponents, but specifically fractions with both an integer in the numerator and denominator. So with that said, let's go ahead and get started with the section. So we're going to start off the section with the key underlying concept of all of section P3. Everything else will be built from this, and that is essentially the idea that a fractional exponent is just a different way of writing a root or a radical. And so what we see here is that if n is a positive integer, and if a is positive, it can be anything, any real number, then a to the 1 over nth power is the same as the nth root of a, and we often write it in this radical format. And for the most part, people are really familiar with the radical format with square roots, cube roots, all of that good stuff, but really it is just shorthand for writing these fractional exponents. Roots are just exponents, and so because of that, they'll end up inheriting a lot of the properties from exponents. All right, and so again, our first key idea from this section is that a to the 1 over nth power is the same as just the nth root of a. So if it were the 1/2 power, that would be a second root or a square root. If it were a 1/3 power, that would be a third root or a cube root, so on and so forth. Now a little bit of terminology before we move on. The expression nth root of a, anytime you're dealing with roots at all, is called a radical. So we don't call them roots specifically. We can use that as shorthand or colloquial term, but they're technically called radicals. On top of that, with a lot of our applications, we specifically need to refer to the stuff inside of the root. And if that's the case, we call that the radicand. So a in this case would be the radicand because that's everything inside of the radical. So let's take a look at an example involving these two alternate notations, fractional exponents and radicals. As we get to examples in this class, what I would like you guys to do, and I'll try to remind you, but I'm inevitably going to forget sometimes, is to pause the video and see if you can work through the example yourself. It's okay if you get stuck on the problems because then I'm going to work through it afterwards, and you can use that as a chance to see what you did wrong and correct issues as they arise. And so I think you'll get a lot more mileage out of the examples if you try to work through them yourself before you watch me work through them. So with that said, try pausing the video now and see if you can work example 1. All right, so the problems in this section start out pretty straightforward. In part A, we're asked to evaluate 4 to the 1/2 because the denominator of the fraction is 2. That is a second or square root, so that's just square root of 4 or 2. Similar for part B, 27 to the 1/3. The denominator of the fraction is a 3 this time. So this is a third or a cube root. So this is cube root of 27. And since 27 is 3 cubed, the cube root would just be 3. Now part C is a little bit on the trickier side, and that's because you have to ask yourself, does negative 144 to the 1/2 mean the square root of negative 144 or negative square root of 144? One of these is correct, one of these is incorrect. And so this leads to a pretty frequent issue that we see with students in algebra where they're not sure how to handle roots or exponents in general, honestly, and negative signs out front. And the trick to remember is that this is actually just related to the order of operations, PEMDAS. Anytime you see a negative sign like this, you can think of that as -1 times 144 to the 1/2 power. A negative sign lives in the multiplication level in the order of operations. And so because exponents have a higher priority than multiplication, the -1 sits out front while you take the square root of the 144 first. So the correct format here is negative square root of 144. And because 144 is 12 squared, this evaluates out to a -12. So the minus sign out front just kind of tags along for the ride. So you might ask then, is there ever a situation where the negative sign would come inside of the radical or inside of the exponent if we're dealing with non-fractional exponents? And the answer is yes. There's only one thing that is higher priority than exponents in the order of operations, and that's parentheses. So if you wanted to create something like square root of -144, that would actually look like this. You would have a negative sign in parentheses and then the whole thing raised to the 1/2 power. Whereas negative square root of 144 is what we saw in this problem. No parentheses to be found. So be a little bit careful with that distinction. So far, we've considered the specific case a to the 1/n power. Let's take a look now at what happens when the numerator of the fractional exponent is something other than 1. So this is the more general case of a to the m/n power. Before I show you how we handle this, let's lay a little bit of groundwork. The first is a property of exponents. If you have a raised to the mth power in parentheses, which is raised again to another power, the way we simplify that is you would multiply the two exponents together. I'm going to be making use of this property, but I'm actually going to be using it in reverse. So I'm going to be taking two things multiplied together and splitting it up into a power raised to another power. The other really basic fact that I'm going to make use of here is the fact that m times 1/n gives us the fraction m/n. So let's use these two properties together to break this a to the m/n down into the specific 1/n case that we were looking at earlier. So by property of exponents, a to the m/n, again, because m/n is m times 1/n, we can write that as a to the mth power raised again to the 1/nth power. Right? If you were to reverse that simplification, you would multiply those two exponents together, which would take us back to where we started. But remember, the 1/nth power is the same as the nth root. So we would take this entire thing in parentheses, a to the mth power, and we would put it all under an nth root. So in other words, what a to the m/nth power is telling you is that you're going to raise the base a to the mth power, that's the numerator of the fraction, and then you're going to take the nth root, that's the denominator of the fractional exponent. But that's not the only way we could write this. And it's due to the fact that multiplication with real numbers is commutative. So m times 1/n is m/n, but if you swap the order, and you did 1/n times m, that would give you the same thing. That's still m/n. So let's split this up in the other order. This time I'm going to write it as a to the 1/nth power in parentheses raised again to the mth power. So same as before, if you tried to simplify this, you would multiply the two exponents together, which would still take us back to a to the m/n, where we started. This time around, though, the order that we're doing the operations in is different. So in the parentheses, we have a to the 1/n, which is the nth root of a, but that's still raised to the mth power. And so we get the nth root of a raised to the mth power. And so the key takeaway here is that when you're dealing with a fractional exponent m/n like this, it's telling you to do two things. You're going to raise the base a to the mth power, and you're going to take the nth root. of a. And the really powerful thing, and what these two different forms show us, is that the order you do it in doesn't matter. You could raise it to the nth power first, and then take the nth root, or you could take the nth root first, and then raise it to the nth power. It doesn't matter, as long as you perform those two operations. The numerator is a traditional exponent. You just raise it to that power. The denominator is the index of a root. You take that root. Generally speaking, if you're evaluating these without a calculator, which a lot of the problems we work can definitely be done without a calculator, you'll usually take the root first if it works cleanly, and then raise it to the power, because that just gives you smaller numbers to work with overall. So in example 2, we're going to do some more evaluation, but this time where the numerator of the fractional exponents is not 1. And so once again, try pausing the video here and see if you can find the answer to example 2. All right, in part A, we've got negative 27 to the 4/3 power, making note of the fact that the minus sign is in parentheses this time around. So it will be getting affected by the exponent, unlike our negative 144 to the 1/2 we had in example 1. And so our exponent in this case is 4/3, meaning we need to do two things to this negative 27. We need to raise it to the 4th power, and we need to take the cube root. And the order doesn't matter. However, because we can take the cube root of negative 27 cleanly, that's where I'm going to start, just to make the number smaller before I raise it to a power. So I'm going to choose the order where I take this negative 27, I'm going to take the cube root, and then I'm going to raise it to the 4th power. Now, even roots of negative numbers are a little bit weird, and we'll introduce the concept of complex numbers later on in section P7. You end up having to use imaginary eyes. But odd roots of negative numbers work just fine, because negative 3 cubed, negative 3 times negative 3 times negative 3, would give you negative 27. So the cube root of negative 27 would be negative 3, but now we want to raise that to the 4th power. So that would be negative 3 times itself 4 times. And so let's see if we can simplify this without a calculator. So I'm going to choose to multiply pairs of these negative 3's together. Negative 3 times negative 3 is 9. So we can simplify this to 9 times 9, which would give us a positive 81. For part B, we've got 4 to the negative 3/2 power. Now, it's important that we know how to handle negative exponents. If you've got a to the negative nth power, that's the same as 1 over a to the positive nth power. So 4 to the negative 3/2 power would be the same as 1 over 4 to the positive 3/2 power. And then we can just evaluate this denominator the same way that we handled part A. So this 4 in the denominator, we need to do two things. We need to cube it, and then we need to take the square root. And once again, the square root happens to work out cleanly, so I'm going to start with that. So this would be 1 over the square root of 4 cubed, which of course would be 1 over 2 cubed, which would be 1 over 8. Now, be a little bit careful with the rational exponents that we're working with here, and do not get them mixed up with negative exponents. That's a common mistake that tends to crop up when working with algebra, and it's because negative exponents are related to fractions, but it's not quite the same in reverse. Or what I mean by that is fractional exponents are not related to negative numbers in any way. So I think sometimes it just gets a little bit backwards in people's heads. Remember, negative exponents are related to reciprocals, whereas fractional exponents, in particular any exponent with a denominator, is related to radicals. Two completely different concepts. So let's jump straight into example 3, where things get a little bit more abstract. We're going to start introducing some letters. This is an algebra class after all. And we'll also be introducing or expecting you to use more properties of exponents in the problems as well. If you're a little bit rusty on your properties of exponents, I highly recommend that you go back and review section P2, the one preceding this section, P3, where those properties are first introduced. So once again, try pausing the video here and see if you can find the answers to example 3. Well, part A and B in this example are pretty similar to each other. The only difference is that in part A, the base is the letter A, whereas in part B, the base is just a number 4. But in either case, it is two exponential expressions multiplied together with the same base, matching bases. So the way we handle that by property of exponents is that we add the exponents together. So this would be the same as A to the 3/5 plus 7/5. Now that these fractions are in the same exponent together, you can perform just basic math on them. So 3/5 plus 7/5 would add to give you 10/5. And if your fractional exponent is capable of reducing, you can do that as well. And 10 divided by 5 would give us 2. So the simplified form of this expression, a to the 3/5 times a to the 7/5, is actually the same as just a squared. We can't take it any further than that because we don't have a number here, right? We don't know what a is, so we can't square it. So this is as good as it gets. Part B is really similar. We've got the common base of 4 between the two expressions, and so we would just add the exponents together. 3/4 plus 3/4, which would give us 6/4, which is a fraction that reduces. You can divide both the numerator and denominator by 2, so that would be the same as 4 to the 3/2 power, which is something we actually saw in the previous example. It was just to the negative 3/2 power. We don't have to flip it this time. So I'm going to take the square root of 4 first, which would give us 2, but then we still need to raise it to the 3rd power, and 2 cubed would give us 8. Now another alternate way you could work example B is that 4 to the 3/4 power times itself would be 4 to the 3/4 power squared. So that's another way you could write the expression in part B. And then also by property of exponents, that would just be 4 to the 2 times 3/4 power, which would be 4 to the 6/4 power. And then at that point, the problem would work out the same way as we did previously. In part C, we've got what initially at least looks like a much more complicated expression, x to the 6th power times y cubed divided by z to the 9th power, in parentheses, all raised to the 1/3. So exponents distribute across multiplication and division. No problem. It's addition and subtraction where exponents get stuck and things start getting tricky and you have to do things like foiling. So again, this is just properties of exponents from section P2. If you want to raise a fraction to a specific exponent, you're going to raise the numerator to that exponent and the denominator to that same exponent. Exponents distribute across division. And then in the numerator, because this is still multiplication, that exponent of 1/3 will distribute to each of those terms as well. So this is x to the 6th to the 1/3 times y cubed to the 1/3, still divided by z to the 9th to the 1/3. Now we can simplify each of these expressions by using the power of a power rule, right? You have one exponent in parentheses raised to another exponent, you multiply them together. And I'm just going to simplify in one step from here on out. So for the x in the top left, we've got x to the 6 times 1/3, which is the same thing as 6 divided by 3, or 2. So that simplifies to x squared. Similarly, y cubed to the 1/3 would be y to the first power. 3 times 1/3 would give us 1. And anything to the first power is just itself. So you don't even have to write that exponent anymore. And then in the denominator, we've got z to the 9th to the 1/3. 9 divided by 3 would give us c cubed. And so that would be the simplified form of the expression in part C. Well, since we just worked an example involving the fact that exponents distribute across multiplication and division, this is a good time to introduce the product and quotient rules for radicals as well. Because remember, radicals are exponents. And so they inherit many of the same properties. And I'm going to walk you through the derivation of these because they're pretty simple. So in part 1, we've got what's called the product rule for radicals. And that's that if you have the nth root of a product, a times b, is just the nth root of each part of the product. And the reason for that is because this term on the left, nth root of a times b, by definition, is just a times b all raised, so in parentheses, to the 1 over nth power. But by properties of exponents, that 1 over nth exponent would distribute to both terms in that product. And so then we just reverse the definition. A to the 1 over nth is nth root of a, and b to the 1 over nth is nth root of b. So since exponents distribute across multiplication, so do radicals. And in fact, this is what we use to simplify radical expressions, which you guys hopefully have a little bit of an experience with. So we'll work an example with this a little bit later on. But let's say you wanted to simplify the square root of 12. Well, we can't take the square root of 12 exactly. It's not something squared. But we can simplify if we can pull a perfect square out of it. Because 12 is 4 times 3. And we can take the square root of the 4. If we apply this product rule, this would be the square root of 4 times the square root of 3, or 2 times the square root of 3. So in other words, you can essentially take the square root of the stuff you can and pull it outside of the radical, while the stuff you can't is still trapped inside. All right, so that's the product rule for radicals. The same thing holds for fractions as well, and it's by the same logic, because this would be a over b to the 1 over nth power. That 1 over nth power would distribute to the numerator and denominator. And so you can just take the nth root of the numerator a and take the nth root of the denominator b. Since exponents distribute across addition, so do radicals, because radicals are just exponents. So let's make use of those product and quotient rules to simplify some more expressions, which is ultimately what every problem in this section boils down to in the end. So once again, try pausing the video here and see if you can find the answers to example 4. All right, so these problems are pretty straightforward as long as you know the product and the quotient rules. So for part A, we've got the cube root of 125 times a to the 6th. So this is a product, 125 times a to the 6th power. So we can break this up as the cube root of 125 times the cube root of a to the 6th. And because 125 is 5 cubed, 5 times 5 would give you 25, times 5 again would give you 125. That works out nicely. Cube root of 125 would be 5. But let's talk about how to handle this a to the 6th in the cube root. And the trick to seeing how this simplifies is to go back to writing it as a fractional exponent. So this is a to the 6th power inside of a cube root, which is the same as raising it to the 1/3 power. And so because this is, again, a power of a power, we multiply those together. 6 times 1/3 would be the same as 6 divided by 3. So in other words, you take the exponent inside of the root and you divide it by the index of the root, which is 3 in this case. And so that reduces perfectly to 2. And so in this case, we would get a squared left over. All right, so again, that's worth remembering as a shortcut. You take the power on the inside and you divide it by the index of the root. Part B is a little bit more straightforward. We've got the square root of a fraction. So we're just going to distribute the square root to both the top and the bottom of the fraction. And fortunately for us, the denominator, square root of 16, works out nicely because 16 is 4 times 4. And so this would be square root of 3 over 4. If that square root in the denominator hadn't worked out nicely, then we wouldn't be in what's called simplified radical form, which we'll talk a little bit more about in a minute. And then for part C, we're going to need to apply both the quotient rule and the product rule of radicals. So let's start by applying the quotient rule. We've got the 5th root of a fraction, so we would take the 5th root of the numerator, as well as the 5th root of the denominator. But this 32, or rather negative 32 y to the 5th, is a product. Negative 32 times y to the 5th. So we can break that up even further with the product rule and write that as the 5th root of negative 32 times the 5th root of y to the 5th, still over the 5th root of x to the 20th. And then we can simplify each of these terms individually. So the 5th root of negative 32, that happens to work out nicely because 2 to the 5th power is 32. And similarly, negative 2 to the 5th power is negative 32. And so if we take the 5th root of that, we would get a negative 2 out. It's an odd root, so the negative sign is not a problem. And then once again, for the expressions that we can't evaluate exactly, we're going to take the exponent on the inside, divide by the index, because that's a 1/5 power. And so for the y, we would get 5 divided by 5, which would just be 1, so that's just y to the 1st power. And in the denominator, we would get 20 divided by 5, 20 times 1/5, which would give us x to the 4th power. So now let's talk about what happens when the roots don't work out quite so nicely. And our goal when we are simplifying expressions involving radicals is if we can't get rid of the radicals completely, we at least need to leave our answer in what is called simplified radical form. And so let's talk a little bit about simplified radical form. There are 3 conditions that your expression needs to meet in order to be considered in simplest form. The first is that there is no perfect nth power as a factor of the radicand for an nth root, meaning there's nothing you can pull outside of the square root. So the example we looked at earlier of square root of 12 is not considered simplified radical form because there was a perfect square that we could pull out. If that's square root of 4 times 3, 2 square roots of 3 would be the simplified radical form for that expression. Secondly, and in fact both parts 2 and 3 are related to fractions, in part 2, no fractions can be inside of the square root as part of your final answer. So the problem we worked on the previous example of square root of 3/16, you would never leave your answer like that because that's not simplified radical form, unless you're specifically told that you can leave your answer like that. All right, so anytime you have a fraction inside of a square root, you would break it up using the quotient rule. in order to get simplified radical form. As part of that process, however, you often lead into the conflict in part 3. And the final condition we need to meet, and this is often the trickiest to figure out how to fix, is that you can't leave any radicals in the denominator of an expression. So let's say we had the square root of 2/5. Well, that's not simplified radical form because it doesn't meet condition 2. There's a fraction inside the radical. So the first thing you might do is, much like the previous example, break it up. Square root of 2 over square root of 5. The problem is that now the denominator square root of 5 doesn't work out cleanly like square root of 16 did. But this now violates the third condition for simplified radical form. There's a radical in the denominator. So we're going to have to get rid of that in other ways. And we're going to rationalize the denominator in order to accomplish that. We're going to multiply the bottom of this fraction by something in order to allow us to take the square root cleanly. And so I'm actually just going to multiply by another square root of 5 in this case in order to make it a perfect square. But we don't want to change the value of the expression. If I multiply something into the denominator, it's a different fraction now. I don't want to do that. So in order to keep everything balanced, we need to make sure we multiply the top of the fraction by the same thing. Because when you multiply by square root of 5 over square root of 5, both the top and the bottom, it's the same as multiplying by 1. It doesn't change the value of the expression. It's important that we preserve the value. We don't change it as part of our simplification. And so we're going to multiply both the top and bottom by the same thing, square root of 5. So the top now, square root of 2 times square root of 5. We'll talk a little bit more about this later on, but I can give you guys a taste of how we can simplify that now. If you just use the product rule for radicals that we looked at earlier, that said that radicals distributed across products in reverse, then we can actually take what's inside these square roots and multiply them together. So square root of 2 times square root of 5 is actually square root of 10. And that doesn't have any perfect squares in it. 10 is just 5 times 2. So there's nothing we can pull out of that. And now the denominator would be square root of 5 squared. And those essentially just cancel each other out because the square root is a 1/2 power. Multiply that by 2, the other exponent, and you just get 5 to the first power. So let's look at some more examples similar to this one where we're trying to take some expressions and write them in simplified radical form. All right, so once again, our goal here is to write everything in simplified radical form. So try pausing the video here and see if you can find the answers to at least this part of example 5, because there's actually more than 4 parts to this one. All right, so part A is similar to the square root of 12 that we worked a couple times previously. We just want to simplify square root of 20. And so our goal is to see if there's any perfect square that we can divide cleanly out of this. Now, you can absolutely brute force one of these problems. It's not a big deal. And you basically just think about a list of perfect squares and see if any of them would divide cleanly out of the number you're trying to simplify. So some perfect squares involve 4, 9, 16, and 25. And on top of that, you can always stop checking after you get to half of whatever the number is, because the biggest thing you could ever divide out of this, it would still have to be multiplied by 2. So in this case, the only things we would need to check is 4 and 9. And in fact, you can divide 4 cleanly into 20, and that would leave you with 5 left over, and that's because 20 is 4 times 5. And so now we can take the square root of the 4, which is 2, but the 5 is still trapped under the square root. And so that would simplify to 2 square roots of 5. Now there is another method that you can use to simplify radicals like this. It's a little bit slower most of the time, but it works for higher order roots a little bit better than this, I think. and that is using something called the prime decomposition of a number, which is a really fancy term, but all it's basically saying is you keep dividing the number out until you get it down into basic parts that can't divide any further, prime numbers. So in this case, think about what you could divide 20 into. 20 you could write as 2 times 10, but 10 you can break up further because 10 you could write as 2 times 5. And none of these numbers you could write as a product of integers anymore. 2 and 5 are both prime numbers. So that's as far as you can break it down. And so once you've got a number down to its prime decomposition, you're just looking for, in this case, because it's a square root, pairs of numbers, perfect squares. Because 2 times 2 is 2 squared. And so you can take that square root, which would get you to 2 square roots of 5. Before we move on to part B, let me show you how this would work with a different index for the root. Like, let's say we wanted to simplify a cube root. And so let's say we wanted to see if cube root of 24 would simplify at all. Again, you could actually just look at a list of perfect cubes, try to divide them out. Again, I think that's the fastest way to work the problem. All I'm doing here is showing you an alternative. Well, let's think about how far we could break 24 down. 24 you could write as 2 times 12, but 12 you can break down further because that you could write as 2 times 6, and then 6 you could break down because that you could write as 2 times 3. And so what you end up with is that 24 is 2 times 2 times 2 times 3, or 2 cubed times 3. So you actually could simplify this because you have a triple of numbers in this case, right? 2 squared is not good enough to pull out of a cube root. You need 3 of them this time around. And so the cube root of 24 you could write as 2 cube roots of 3. And again, if you were looking at a list of perfect cubes, you would find the thing you could divide quite early on, because 2 cubed is equal to 8, and 8 divides cleanly into 24. All right, so with that little aside done, let's go back to working example 5, and let's take a look at part B. We want to evaluate the square root of 24 times x to the 8th times y to the 9th. All right, well, by the product rule we talked about earlier, we can just focus on taking the square root of each piece of this. Or in other words, just thinking what all we can pull out of the square root. So starting with the number, square root of 24, we'll see if we can handle that similar to the way we did part A. Are there any perfect squares that we can pull out of that? And in fact there is, because that one is also divisible by 4. So that would be the square root of 4 times 6. I'll simplify that in the next step. X to the 8th is actually going to work out cleanly already, because let's think about why that is. Remember, a square root is a 1/2 power, so you would divide the exponent on the inside by 2, and because 8 is an even number, that works out really nicely. That's just x to the 4th. Y to the 9th, on the other hand, doesn't work out quite so well. If we tried to simplify that, 9 is not divisible by that root of 2. That's the same as just y to the 9/2 power. Which, while it's not wrong to write it as y to the 9/2 power, that's not what they're looking for here in simplified radical form. We want to take as much out of the square root as we can and leave everything else alone. And so what I'm going to do is I'm going to write y to the 9th as y to the 8th, an even number, times y. And so let's see what we get. For the numbers, that gives us 2 square roots of 6. The x came out cleanly, that's just x to the 4. And for the y's, square root of y to the 8th is similarly y to the 4th but we still have one y trapped inside of the square root. Now the very last thing I'm going to do to combine all this together and to simplify is I'm going to go ahead and combine the square roots back together again using the reverse of the property that we started out with. All right, if I've got square root of 6 times square root of y, I can write that as square root of 6 times y. So I'm going to collect all of the things outside of the square root. We've got a 2, an x to the 4th, a y to the 4th, and this is times the stuff that's still trapped inside of the square root, which would just be 6y. The other way of thinking about this problem, and again, it's just a different way of getting to the same result, is you could have broken up everything inside of the square root without breaking it up like this in the first step. So you could have written 24x8y to the 9th as 4 times 6 times x to the 8th times y to the 8th times y. And then just taking everything that you can take the square root of cleanly out. Square root of 4 is 2. Square root of x to the 8th is x to the 4th. Square root of y to the 8th is y to the 4th. And then everything else, the 6 and the y, is still left inside. And so that's kind of a shortcut way of thinking about the problem. Part C is a little bit simpler overall, I would say. Our main issue here is the square root in the denominator. We don't want to see that. And so we need to rationalize this, similar to the example we worked on the last slide. So I'm going to multiply the square root of 3 times itself to square it away, but whatever I multiply the denominator by, I'm going to multiply the numerator by the same thing to preserve the value of the expression. And so in the numerator, we've got 9 times the square root of 3, which is just 9 times the square root of 3. And in the denominator, we're going to have the square root of 3 times itself, square root of 3 squared, which is just 3 to the first power. The square and the square root cancel each other out. Now there is a little bit more we can do here because we can reduce this fraction. Because 9 can be divided by 3, we can divide a 3 out of it using the 3 in the denominator, and this reduces to just 3 square roots of 3. All right, for part D, we've got a fraction inside of a radical, not simplified radical form. So we'll start by breaking it up as the square root of 3y over the square root of 20. Now the problem is that we've got a square root in the denominator, and we don't like that. So now this becomes more like part C that we just worked. Now you could jump straight in and start multiplying by square roots of 20 on top and bottom. The problem is that you end up with not super large numbers if you do that, but you will end up with a fraction that can be reduced. And you'll also end up having to simplify the radical on the numerator if you do that. Instead, if you notice that your square root in the denominator happens to be something that you can simplify, like we did in part A here, you should simplify that first and then rationalize. It'll save you a little bit of work in the end. So because 20 is 4 times 5, square root of 20 would be 2 square roots of 5. And now we're fine leaving the 2 in the denominator. That's not a problem. We can just worry about the square root of 5. So that gives me a much smaller number to multiply by in this case. So if I multiply both the top and the bottom by square root of 5, let's see what happens. Again, I'm going to use that same trick we've used a couple times now, where if we want to multiply 2 square roots together, we're just going to use the reverse of the product rule. We're just going to multiply the stuff inside of the roots. So 5 times 3y would be 15y. And now in the denominator, we're going to get 2, that 2 out front is still there, times the square root of 5 times the square root of 5, or square root of 5 squared, which is just 5. And so now that that 5's out of the square root, we can multiply it with the 2, and this would be the square root of 15y over 10. Now, just to show you an alternate way to work that, if we had just left it as square root of 20 in the denominator and rationalized it by multiplying both the top and bottom by that, I'm actually not going to multiply those square roots in the top together this time for reasons you'll see in just a second. The denominator would just be 20, but then you would still have to simplify the radical on top. There's still a perfect square. And square root of 20 is still 2 times the square root of 5. But now the 2 on the top will divide into the 20 on bottom, and you still ultimately end up with the same thing, just through a different method. In this case, it's about the same amount of work either way, but I think the more you can simplify the square root on the bottom, the bigger the number inside is, the more advantageous it is to simplify first and then rationalize, as opposed to rationalize first and then simplify. In the final two parts of example 5, we've got the same idea. We want to write the problems in simplified radical form. The only difference is you'll notice that these are now cube roots instead of square roots. And that tends to trip a lot of students up because they don't recognize that you can't simplify a cube root in a denominator the exact same way that you do a square root. So let's illustrate this point with part E. So if we want to simplify the cube root of 1/2, we would start by applying the quotient rule. Cube root of 1 over cube root of 2. Cube root of 1 is, of course, just 1. In fact, any root of 1 is just 1. Please make note of that. If you ever leave anything as cube root of 1, fifth root of 1, whatever, I will take points off for that. It is a little bit of a pet peeve of mine. That is not simplified form. I still have students leave those in calculus classes sometimes, which is just not okay. It's important to know that any root of 1 is just 1. The cube root of 2 on the bottom does not work out cleanly. So this is not simplified radical form because we have a root, a radical, in the denominator. The problem is that when we get to this point, a lot of times students will just try to multiply by cube root of 2 over cube root of 2, which does not work. And the reason for that is because cube root of 2 times cube root of 2 is cube root of 2 squared. A square and a cube root do not cancel each other out the same way a square and a square root does. So as we move into higher order radicals, I recommend you again think of this as multiplying the things inside of the radical, the reverse of that product property that we looked at earlier. And you need to think about what you need to multiply in order to make the inside a perfect cube. So I'm going to multiply this denominator by, it has to be the same index. All right, this property doesn't work in reverse unless the indexes are the same. So I'm going to have to multiply by a cube root, but I want to make the inside a perfect cubed. And in this case, because I've already got a 2, the smallest perfect cube I can make is 2 cubed. So if I have 1 2 inside of the cube root right now, I essentially need to multiply in 2 more in order to get a perfect cubed in the denominator. So it's actually the cube root of 4 that I need to multiply both the top and bottom by. And so that would give me cube root of 4 in the numerator and cube root of 8 in the denominator, which is, again, 2 cubed. That was the whole reason we chose to multiply by 4. And so cube root of 8 evaluates out to just 2. So take that concept, the idea of multiplying in a number in order to make the denominator a perfect cubed, and see if you can use it to find the answer to part F. Try pausing the video here. All right, so once again, we're going to start with the quotient rule. This is a cube root of 3 over a cube root of 5a to the 4th. And I need to figure out what cube root I need to multiply the bottom by to make everything on the inside a perfect cube. So I need to do two things here. I need to make the number a perfect cubed, and I need to make this expression of a perfect cube. I can't leave any cube root left over in the denominator. Well, the 5 works out very similar to what we did in part E. So the smallest perfect cube we can make with 5 is 5 cubed. So I need to multiply it by another 5 squared, or in other words, 25. With the letter, you need to be a little bit careful because remember, we handle those differently with the roots. You take the exponent on the inside and you divide it by the index of the root. So the cube root of a to the 4th is the same as a to the 4/3, 4 divided by 3. So what we need to do is to make this a on the inside a power that is divided cleanly by 3. In other words, a multiple of 3. So the smallest number bigger than 4 that we can divide by 3 evenly would be 6. A to the 6/3 would just be a squared. So that's my target here. So if I want to make a to the 4th a to the 6th, I need to multiply it by an extra a squared. Because remember, property of exponents, if you multiply two exponential expressions with the same base, you add the exponents together. So I need to multiply in an extra a squared to make that a perfect cubed. Whatever I multiply the denominator by, I multiply the numerator by the same thing. And be careful, it's really easy to forget to write the index, but if you do, you're technically writing square roots at that point. The problem's wrong. So it's just something to be careful not to lose track of. All right, so once again, to simplify the numerator, I'm just going to multiply the things inside the roots together. So 3 times 25a squared. 25 times 3 would be 75. So that would just be the cube root of 75a squared. And in the denominator, we would get the cube root of 125a to the 6th, which is a perfect cubed. We specifically made it as such by picking what we multiplied by. So that would be 5a squared. All right, so be a little bit careful. Trying to get simplified radical forms with roots other than square roots is a little bit foreign to a lot of students. It takes a little bit of practice to understand the procedure that you need to follow in order to make it work. So now let's talk about operations with radical expressions. So if you have multiple roots, multiple radicals, how can you combine them together in our traditional operations? The operations you guys are used to with real numbers are addition, subtraction, multiplication, and division. And so that's what we're talking about here. So to start off with addition and subtraction, in order to add or subtract radicals, they have to be exactly the same radical. Think of them like a variable. So for example, if you have square root of 2 plus 2 square roots of 2, think of that like x plus 2x. If you have 1x and you add 2 more to it, that gives you 3 x's in total. Same thing holds here too. If you have 1 square root of 2 and you add in 2 more, you end up with 3 square roots of 2. That only works though if they are exactly the same. So for example, if you've got something like square root of 2 plus square root of 3, you just cannot simplify that. Be careful. People get used to how nice exponents work with multiplication and division, and we'll talk a little bit more about that in a second, but a lot of times students will make the mistake of thinking square root of 2 plus square root of 3 is the square root of 5. That is absolutely not the case. If it worked that way, we wouldn't need a thing such as foiling. So please, please, please keep that in mind. Very important, very common mistake. The same thing would hold true for subtraction. I didn't specifically write subtraction examples here, but similarly, square root of 2 minus 2 square roots of 2 would leave you with a -1 square root of 2. Works the same way. And similarly, you can't subtract unless they're also exactly the same, like radicals. Multiplication and division works much more nicely with exponents, and therefore with radicals as well. And multiplication we've actually done several times already. These are really just reverses of the product and quotient rules that we looked at earlier in the section. So if you've got a product of two roots with the same index, that's important because our product rule indicated the same index when we broke it up. Then you can just multiply the stuff inside together. So cube root of 2 times cube root of 3 is just cube root of 6. And division works the same way. If you add square root of 10 divided by square root of 2, if you just reverse the quotient rule, that would be the square root of 10 divided by 2, which is just square root of 5. So you can just divide the stuff inside of the roots. Again, as long as the indexes match, these are both square roots. If you had different indices, so something like square root of 2 times cube root of 3, because it's a square root and a cube root, you cannot multiply the stuff inside together. You can't simplify that, at least not yet. We'll talk about a way to combine these together at the end of the section, but it's not just straightforward multiplication. So now let's try simplifying some radical expressions with some operations thrown into the mix. So once again, try pausing the video here and see if you can find the answers to example 6. Now part A and B have a little bit of a trick to them, so if you had trouble with that, it's not too big of a deal. Once I show you the trick, you'll probably be able to figure out the other one pretty easily, so maybe try pausing again after part A if you couldn't figure out either one. So we said on the previous slide that you can only add or subtract radicals if they're exactly the same. None of these are the same. And again, please do not write that as square root of 8 plus 20 minus 45. It does not work that way. But what we can do is each of these square roots simplify on their own. So let's take care of that first. 8 you can write as 4 times 2. 20 you can write as 4 times 5. And 45, a perfect square you can pull out, is 9. 45 you can write as 9 times 5. And so if we simplify these, take the square root of the 4's and the 9, you would get 2 times the square root of 2 plus 2 times the square root of 5 minus 3 times the square root of 5. And while not all of these radicals are the same, some of them are. So we can add or subtract the ones that are now the same. And so this square root of 2 wouldn't combine with anything else. There are no other root 2's. But if we have 2 square roots of 5, and then we do minus 3 square roots of 5, those two could combine to give us a negative 1 square root of 5. And so this would simplify to 2 square roots of 2 minus the square root of 5. So again, if you had problems with parts A and B, try pausing the video here and see if you can find the answer to part B now. Well, it's a very similar process, and I'm going to go ahead and simplify these radicals a little bit faster than the previous ones. 18 is 9 times 2, so that would be 3 square roots of 2. 50 is 25 times 2, 5 squared, so that would be 5 square roots of 2. 12 is 4 times 3, so that would be 2 square roots of 3. And 75 would be 25 times 3, 5 squared times 3, so that would be 5 square roots of 3. And again, they won't all combine, but some will. 3 square roots of 2 plus 5 square roots of 2 would give us 8 square roots of 2. And 2 square roots of 3 minus 5 square roots of 3 would give us a negative 3 square roots of 3. Parts C and D both deal with multiplication. For part C, We've got negative 2 square roots of 3 times 5 square roots of 6. Let's just think about what this means. That's a negative 2 times the square root of 3. There's no addition or subtraction here, so the parentheses aren't adding anything. That's going to be times 5 times square root of 6. But because multiplication is commutative, I can shuffle the order around here. I can write that as negative 2 times 5 times the square root of 3 times the square root of 6. So in other words, you can multiply the numbers together and you can multiply the roots together. So what we would end up with in this case is negative 10 times the square root of 6 times 3, which is 18. But we're still not quite done yet because square root of 18 will now simplify, because 18 is 9 times 2. That would turn into 3 square roots of 2, and then one more time you can multiply the numbers together. So this would give us a negative 30 square roots of 2. Now with part D you have options. Anything squared is times itself. So you could just write negative 5 square roots of 3 twice, and then it becomes exactly like problem C. You would work it the same way. Or you could just use properties of exponents. And exponents just distribute to each term in a product or a quotient. And so you could also write this as negative 5 squared times the square root of 3 squared. Negative 5 squared would give us a positive 25. Square root of 3 squared, again, square root is a 1/2 power. That cancels out with the exponent of 2. So that's just times 3. And so this whole thing is 25 times 3, or 75. For our final type of problem in the section, this is one of the longer sections in the course, let's talk about how we combine roots with different indexes. So as mentioned earlier, cube root of 3 times square root of 2, you can't just multiply together the stuff on the inside because the indexes are different. There is still a way you can combine this together though. And the trick is to write the roots as fractional exponents again, and then get a common denominator for the fractional exponents. In other words, we're going to turn these into a common root of a different index. So let me show you what I mean with part A of example 7. Cube root of 3 you could write as 3 to the 1/3. Parentheses aren't really adding anything there. And square root of 2 you can write as 2 to the 1/2. So what I'm going to do is I'm going to get a common denominator between these two fractions. And the common denominator between 3 and 2 is, of course, 6. So I'm going to multiply the fraction on the left by 2 over 2. That's the same as 3 to the 2/6 power. The fraction on the right I'm going to multiply by 3 over 3. So that's 2 to the 3/6 power. And now I'm going to write it back in radical form again. But I'm going to go ahead and include the numerator as powers. So when we were talking about options for handling a to the m over n before, I'm going to include the power inside the root this time around. Because again, I want to combine these two terms together. So 3 to the 2/6 power, I'm going to write that as the 6th root of 3 squared. This will be times 2 to the 3/6 power, or the 6th root of 2 cubed. And now these are like indexes. They're the same. They're both 6 roots. So now we can just multiply the stuff inside. This would be the 6th root of 3 squared times 2 cubed. And now we can simplify the stuff on the inside. 3 squared is, of course, 9. 2 cubed is 8. And 9 times 8 would give us 72. So you can combine those together to the 6th root of 72, but make note that it's not just multiplication. and the root that we ended up with wasn't the same as either of the roots that we started with in this case. So now that you've seen an example, try pausing the video and see if you can find the solution to part B of example 7. All right, so by a similar process, cube root of 3 would be 3 to the 1/3. 4th root of 4 would be 4 to the 1/4. We need a common denominator between 3 and 4, which is 12. So I'm going to multiply the one on the left by 4 over 4. It's 3 to the 4/12. The one on the right by 3 over 3. That would be 4 to the 3/12. Now turn them back into the roots. That's the 12th root of 3 to the 4th times the 12th root of 4 cubed. So that's the 12th root of 3 to the 4th times 4 cubed. And I'm going to multiply this out to get one big number. But before you do, note that there's no way that this would simplify after the fact. You don't even have to consider it. Because to pull something out of the 12th root, you would have to have a perfect 12th on the inside. And at most, you could break the 4 down into 2s. 4 is 2 squared. And that would be 2 to the 6th. So you've got 4 3s and 6 2s if you broke this down all the way. There's no way you're getting a perfect 12th out of this thing. And so I'm going to use a calculator to help out with this because these are relatively large numbers. And so if I do 3 to the 4th times 4 cubed, that would give us the 12th root of 5,184. If you did start checking a list of perfect twelfths to see if you could pull something out of this evenly, you wouldn't have to check very long. Because even the first perfect 12th is 4,096, which is bigger than half of this thing. So there's just no way. All right, and so that is it for section P3. Again, one of the longer sections in the course when all is said and done. Also one of the more varied sections, as you can see from the list of types of problems. But ultimately, everything really comes down to just making sure you understand that if you have a rational exponent, it's telling you to do two things: raise it to the nth power, take the nth root, and the order really doesn't matter. So you should be able to evaluate expressions with rational exponents. That's what we did in examples 1 and 2. You should be able to simplify expressions with rational exponents. In other words, when things don't evaluate perfectly, that's what we did in example 3. You should be able to go back and forth between the notation used in this section, between writing radicals as rational exponents or vice versa. So if you've got something to the 1/3 power, for example, you should know that that's the cube root of a, but if you also have a cube root, you should know that that's the same as a 1/3 power. We didn't work any examples specifically focused on this, but these are the underlying concepts in a lot of the other problems that we worked. You should be able to evaluate radicals using the product and quotient rules. Probably one of the trickiest types of problems in this section. You should be able to write an expression with radicals in simplified radical form. Make sure you know the 3 conditions that you need to meet in order to be simplified radical form. There's nothing you can pull out of the root, there's no fractions inside, and there are no roots and denominators. You should be able to perform operations with radicals, addition and subtraction. They have to be the exact same, inside and index. With multiplication and division, it's a little bit more forgiving. They just have to have the same index. And then last but not least, you should be able to combine radicals with different indexes by writing the radicals as rational exponents and getting a common denominator, like we did in example 7. If you guys have any questions about the material, please make sure you let me know, and I will see you in the next video.